previously, we found the electric field around a plane of charge in a rather lengthy process. First, we used the integral method to find the electric field around a ring of charge. Then we used the result from that ring to use the integral method to find the electric field around a disk of charge. And then finally, we used the result for the disk of charge to extend to a plane and find the electric field around a plane. We can use Gauss's law, that the net electric flux is the integral of E dot dA, so the electric field over some Gaussian surface, equal to the charge enclosed by that Gaussian surface divided by epsilon naught. We can use Gauss's law to find the electric field of a plane. The math is pretty easy, but the setup of that Gaussian surface can be a little bit tricky to understand conceptually. So first, let's remember that we typically pick our Gaussian surface to reflect the geometry of our plane. That's what makes the integral easiest to evaluate. So since our plane of charge is just a long line like this, I'm going to use a sheet of paper or a pad of paper to model my plane of charge. For my Gaussian surface, I want it to look like a plane. I'm going to pick it to be a box. So my box, my Gaussian surface, is going to stick out of the top of the plane. Imagine I have the other half of the box. It'll also stick out of the bottom of the plane. So it's going to stick out top and bottom. Now, here's the reason why I'm doing that. My electric field sticks straight out of my plane. So on the top, it's everywhere up. On the bottom, it's everywhere down. Let's just look at the top for a moment. So if I think about the top of my Gaussian surface, the top of my box, the electric field sticks straight up and my area vector sticks straight up. So on the top of the box, the electric field and the area are parallel. The angle between them is 0. On the front of my box, or on the sides of my box, the area vectors stick straight out, the electric field vectors stick straight up, so the area and the electric field on the sides are all perpendicular. So then when I do E dot dA, it's going to be 0. Okay, so if we pick our Gaussian surface to be a little box that sticks up on the top and out on the bottom, then our integral should be pretty easy to evaluate. Okay, I'm going to try and draw that Gaussian surface now. I don't draw the best, so I'll give it a shot here, and then I'll just move to a computer drawn version. So here's a 3D picture of my plane of charge. My Gaussian surface is a box. Try and draw a 3D box that sticks out on both sides. Okay, so there it is sticking out on the front. Here it is sticking out on the back. Okay, pretty hard to see. A 2D view, a little bit easier. There's my box sticking out on the front, and there's my box sticking out on the back. Okay, so we'll work with these two pictures. Well, I guess we'll work with the 2D picture the most, and we'll apply it to Gauss's law, and we'll figure out the electric field around the plane. So our Gauss's law says that the net electric flux is the integral of E dot dA over the entire Gaussian surface, which is a little box, equals Q enclosed by that surface divided by epsilon naught. Okay, so here's my computer generated drawing. Hopefully it's nice and clear. So let's deal with the flux part first. My net electric flux is through the flux through every side of the box. So our box has a top, our box has a bottom, and our box has sides. Let's do the sides part first. So we know our electric field points radially outwards from the plane. Here's our three-dimensional drawing. Here's a side view, and here's a top view. So hopefully this is going to help us see. We'll go on the 3D version first. For the sides of the box, the little area element points straight out. So there's dA for that bit, dA for this bit, dA for this bit, and dA for this bit. Okay, so it's outwards from the side, from every side. If you wanted to draw that on the side view, you could see this bit pretty well, and you could see this bit pretty well. It would be pretty tough to draw it coming out on the sides here because they're kind of pointing right at you. If you wanted to see all four again, you could pretend you're looking at it from the top, and it would look dA here, dA here, dA here, and dA here. In this picture, the electric field is coming towards you because you're looking straight at the surface. In this one, we can see all the vectors the way they are. So these lines, these light pink lines are the electric field vectors. So what we see is that anywhere we're on the side, the electric field is perpendicular to the area. So for the sides, the integral of E dot dA for on any side is equal to the integral of E times dA times cosine of 90 degrees equals 0. Okay, there's the sides done. What about the front and the back, or the top and the bottom? So electric flux for the top part of the box. Let's draw that little bit of dA next. So here's a little bit. I'll try and draw it in 3D. Kind of comes out this way, dA. On this diagram, comes out this way, dA. On this diagram, it would be poking straight out in our face, so I think I won't try and draw that one. So what we see here is that the dA is parallel to the electric field. The angle between them is 0. So the integral of E dot dA for this one is equal to E times dA times cosine of 0 degrees equals the integral of E times dA. The E is constant, so E comes out front, E times the integral of dA, which is E times A. Here in this expression, A means the area of our Gaussian surface. So it's this entire area right here. This is A. So A equals area of the top of the Gaussian surface, which is a box. All right, that leaves us with finding the net electric flux through the back or the bottom, whichever you prefer to call it. So for the back of the box, this is really pretty hard to draw in 3D. So we have a little piece on the back, sticks out this way. A little bit easier with our side view. There's our dA sticking out from the back. So from the back or the bottom, the integral of E dot dA equals, you notice that the dA comes out to the left, the electric field is out to the left. It's the same as it was here. So the angle between them is 0. So our result, dot, 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 will follow the steps from above, equals E times A. So this gives us an expression for our net electric flux. So it's E times A plus E times A plus 0 equals 2 times E times A. Now we know the total flux. We can use that in our Gauss's law, and we'll be able to figure out the electric field expression. We've got our net electric flux figured out. Now for the other part of Gauss's law, we have to figure out Qin. Remember, Qin means the amount of charge enclosed by the Gaussian surface, and the Gaussian surface is my box that sticks out on both sides. Okay, so my plane of charge in our side view, that's this blue plane right here, the dark one. It's our plane right here or our plane right here. So the amount of charge inside our Gaussian surface is the amount of charge on the plane inside the Gaussian surface. So we need to know how much charge is on this. So that's the Q enclosed. However much charge is on this bit is Q enclosed. Also, kind of over on this picture, again, hard to draw in the 3D version. It's however much charge is on that bit of plane. So Qin is going to be the density. Here we have a two-dimensional object, so we're talking about surface area charge density times the area of the plane inside the Gaussian surface. Okay, so density has a symbol of sigma. The area is equal to A that we found in the previous part, sigma times A. So that's our Q enclosed. Let's put this all together with Gauss's law. The net electric flux is the integral of E dot dA, which is equal to 2 times E times A. That's equal to the Q inside, which is sigma times A, divided by epsilon naught. Solve this expression for E. We see that we have an A on both sides, so the area cancels. And it gives us that the electric field around the plane of charge is sigma over 2 epsilon naught. It is a vector, so we have to write that it's out of a positive plane or into a negative plane. Okay, so that was much quicker than the integral method. Let's build on what we've done previously to a new example, an infinite slab of charge. So this is like an infinite plane of charge, except this one isn't thin, it's thick. It has thickness of 2a, that's in this direction. And it's centered in the xy plane. The charge density is uniform. We'd like to find the electric field inside and outside. So first, we know we're going to use Gauss's law. The net electric flux is equal to the integral of E dot dA is equal to the Q inside a Gaussian surface divided by epsilon naught. So let's get a look at our geometry. Let's put on our coordinate system. Let's think about the direction of the electric field, and let's pick our Gaussian surface. Okay, let's put on the coordinate system. Our slab is centered in the xy plane, so I'm going to take positive x to the right. That makes positive y goes back into the page. I'm trying to draw it going through the center there. There's positive y, and positive z goes up. So there's our coordinate system. There's z. Remember that the thickness is 2 times a. It can be a bit tough working with 3D pictures, so let's go over to a 2D picture. X is still going to go through the center, and z is going up through the middle. I won't draw the y-axis since we're in a 2D picture. And the length is 2a, so the middle is right there at z equals 0. The top is there at z equals a, and the bottom is there at z equals minus a. Okay, there's our coordinate system all dealt with. To find our electric field, we're going to have to apply Gauss's law that the net electric flux is the integral of E dot dA equals the charge enclosed by our Gaussian surface divided by epsilon naught. Okay, we need to pick our Gaussian surface. If we want to find the electric field inside our slab or big block of charge, we should pick a Gaussian surface that reflects the symmetry. Since our charge looks like a box, let's pick our Gaussian surface that looks like a box. This is going to follow along what we did for our plane of charge. If we pick our Gaussian surface to be a block inside of our plane, so z less than a, then that'll let us find the electric field inside the block. Or we could pick our Gaussian surface to be a block that extends outside the surface. So this has got a coordinate z greater than a. Greater than a. Let's think about the geometry of the electric field. If our slab of charge is positive, then the electric field is going to point away. So up on top, down on bottom. So let's think about that net electric flux. The net electric flux, we're going to take our Gaussian surface as being three-dimensional. So this is like what we did for the plane of charge. The net electric flux through our Gaussian surface is going to be the flux through the top plus the flux through the bottom plus the flux through the sides. So let's find each one of those terms. Let's do the sides first. The flux through the sides is the integral of E dot dA for each side. dA is the area element coming off the side, so I'll draw one here. Points off to the right here. Oh, sorry, to the left there and to the right here. That's true if it's inside or outside, so either of those surfaces. So our sides are perpendicular to the electric field, so the area vectors point left or right. The electric field points up or down, so they're all perpendicular. That equals the integral of E times dA times cosine 90 degrees equals 0. Okay, what about for the top? The electric field through the top, let's draw our little dA on the top, points straight up. Same is true whether our Gaussian surface is inside or outside. So in both cases, the electric field is straight up, the area vector is straight up. Those two vectors are parallel. So we've got the integral of E dot dA equals the integral of E, the magnitude of E times the magnitude of dA times the cosine of 0 because they're parallel equals the integral of E times dA. Your electric field, as long as we're a constant distance from the center, is going to be a constant, so that's equal to E outside of the integral of dA equals E times A, where A is the area of the top surface of our Gaussian block. So it's the A of this part right here. The electric flux through the bottom is the same as through the top, equals E times A. So then our net electric flux is equal to the flux through the top, E times A, plus the flux through the bottom, E times A. plus the flux to the sides, which is 0. So our net electric flux is 2 times E times A, where A is the area of the top face of that Gaussian block. To find the electric field inside our slab, that's over here in this box, we're going to try and find the electric field at some coordinate Z, where Z, the size of Z, is smaller than the size of the dimension of the plane. In other words, the magnitude of the coordinate Z is less than the magnitude of the size of the plane. Okay, so we already know what the net flux is. Now we need the amount of charge enclosed. Following what we've done in previous examples, the charge enclosed is the density times the volume. That's the volume of a block with thickness 2 times Z. So here's Z equals 0, this is plus Z, and this is minus Z. So our Q enclosed is the amount of charge that's inside this block right here. So if we want to write that down, that's going to be rho. The volume is the length times the width times the height. The length times the width is the area of the face, and the height is 2 times the Z coordinate. Okay, so we've got Z from the middle to the top. Z, the size is Z from the middle to the bottom, so 2Z overall. And then the area of that three-dimensional face is A. Okay, let's put this Q enclosed in our Gauss's law together with our net flux. So the net flux is equal to 2 times E times A. That's equal to the density times A times 2 times the magnitude of the coordinate divided by epsilon naught. We see that we've got A on both sides, so we can divide both sides by A. We've got a 2 on each side, divide both sides by 2. And the size of the electric field is the density times the coordinate divided by the electric field, divided by our constant epsilon naught. Okay, and our electric field is a vector, so I'm going to say outwards from the plane. All right, next we'll do the electric field outside the plane. For our electric field outside the plane, it means that we want the field somewhere up here or somewhere down here. We still need to figure out our Q enclosed, and Q enclosed means how much charge is inside our Gaussian surface. So how much charge is on the part of the slab that's inside the Gaussian surface. All right, Q enclosed, or the Q inside, is going to be the density times the volume of the slab that's inside. So that's going to be the density times the area times the thickness. Okay, and the thickness is 2 times A. Put this together with our Gauss's law. So our net electric flux is 2 times E times A equals our net charge, rho times A over 2A divided by epsilon naught. We've got a 2 on either side, so they cancel out. We've got an area on either side, so they cancel. We're left with our expression for the electric field, which has a magnitude of rho times A divided by epsilon naught and a direction of pointing outward. So there's our electric field around a thick block of charge.